All right, so this is just another sort of supplementary video that I wanted to make to kind of take a bunch of like background stuff about functions that I feel like it would be really useful for people to know and put it all in one place. Um, and it's all stuff that like never really gets taught on its own, I guess. And it's kind of bad. Like I honestly feel like there should be some kind of a class that's just dedicated to like all the odds and ends, like all these like odds and ends about, you know, functions and set theory and stuff like that, that are useful for the working mathematician, that no one, like a lot of people are not really solid with when they come into a class like this, and it's really just unfortunate. But anyway, so these are just some basics. So I'm going to talk about the concepts of injectivity, surjectivity, bijectivity, then also inverses, and restrictions and extensions of functions, and lastly, images and inverse images of sets under functions. Okay, so yeah, they're all like pretty simple concepts, but it would be good to have for you guys to have like a reference for all of it. So okay, let's talk about injectivity, surjectivity, and bijectivity. So surjectivity, bijectivity. Okay, so these are terms that refer to these two refer to properties a function can have, and then bijectivity is just when it has both of these two properties. So let's say, so let f be a function from a set S to a set T, right? So S and T are sets in this case. And you know, it would be good to familiarize yourself with this notation as well. So when we write f colon S arrow T, that means that the domain of S is, or the domain of F, so this is the domain, and this is the codomain, right? Not the range, remember. Codomain is not the range. So this does not mean that every value of T occurs as the value of F at some point in S, okay? So we say F is injective if F of A equals F of B, only when A equals B. Okay, so basically F maps distinct inputs to distinct outputs. Okay, so that's injectivity. We say F is surjective if for all, let's say for all T in the codomain, right? Remember, T is the codomain here. So every value in the codomain is actually the image of some value in the domain. So there exists an S such that F of S equals T. Okay? Then F is bijective if it is both injective and surjective. Okay, so there's a picture, pretty common picture I like to draw, right? So, okay, so I drew this picture that I think kind of illustrates these ideas nicely. So for an injective function, right, you see that, you know, obviously every input gets mapped to some output. Some of the outputs might not ever get hit by an input, but you never have two of these arrows ending up on the same output, right? So no two of these different inputs end up getting mapped to the same output. So that's an injective function. A surjective function, you can have plenty of collisions, right? So like in this one, this guy, the second one here, and then the last one both map to the first one over here. and then also the first one and the fourth one both map to the second one. And then of course there are these two that map to these two over here. And that's okay as long as every value over here gets hit by some arrow, right? And of course, you should imagine that like these sets can be infinite, right? So it's sort of, this picture could be a little bit misleading. Don't pretend that the sets have to be finite, but yeah, this is kind of what it would look like if you just took a handful of points from either set. And then over here we have a bijective function where, you know, each one gets mapped to exactly one point over here, and no points are left out, and so everything, they're sort of matched up perfectly, right? So, okay, this brings us to the concept of inverses. So, sort of formally, we only say f from S to T has an inverse if it is bijective. Okay, but we do kind of fudge this idea in our class specifically, right? In the context of real analysis specifically, there's a little bit of wiggle room here. Okay, but so in this case, so let's just consider this case, right? So in this case, the inverse is a function f inverse from t to s such that f of f inverse of x, or let's say, sorry, actually, let's say it this way. So f inverse of f of s equals s for all s in s, and f of f inverse of s of t, sorry, equals t for all t in t. Okay, so that's when an inverse exists. And so the main thing, so technically this means f must be surjective. Okay, the strange thing about this is the surjectivity requirement, okay? Because like normally, right, like, I don't know, it seems like it shouldn't matter whether every output gets achieved, right? As long as no two inputs go to the same output, then given one of the output values of the function, you can figure out which input it came from, right? It's just that there are some values in this set that just never happen, so those are like, you just toss them out kind of, right? At least intuitively, that's how it feels it should be. The problem is just that in many areas of math, it really pays off to keep track of exactly what you're thinking of as the codomain of your function. And then it really matters like whether the function is actually surjective or not. And if you look at this formal definition, technically, right, the domain of the inverse is supposed to be the codomain of the original function. And if there are values in t that never happen as values of f, right, then f inverse would not be defined at those points. So the domain of f inverse would not be t, it would actually be some proper subset of t. So that's kind of why, like, to make this all work out really nicely is another reason that we require f to be surjective for there to be an inverse, okay? So in real analysis, we fudge this a bit, right? So for example, we consider the function f of x equals e to the x invertible, right? Even though it is not surjective, right? This is because we can invert f as a function from R to the set of real numbers which are positive, right? So this is the true range of the function e to the x, right? So the fact that e to the x is injective means that if we just like throw out all the values from the codomain, like let's say, like here we haven't really specified, we didn't really say what the codomain of e to the x is. Okay, is it R? Is it, you know, what I'll write as R greater than 0? Sometimes people write this set as R greater than 0, right, for the positive real numbers. Okay, so, you know, or is it anything in between, right? We never actually said what the codomain is. And that, like, by our previous formal definition over here, that would actually affect, like, what we consider to be the codomain would technically affect whether the function is invertible, right? And so, like, this has bearing just in the sense that, you know, we have to keep in mind, that the domain of log of x is R greater than 0, right? So even if we ignore, like, a lot of the time, we don't want to actually have to, you know, constantly talk about the fact that technically, you know, we can only invert this if we think of the codomain as being the positive real numbers. So like when we define f as a function, do we specify the codomain as like all of the real numbers or as the positive real numbers? Because if you only specify the codomain as the positive real numbers, then, you know, that could enter into the conversation in other ways where it's like maybe you're trying to combine f with some other function that's just a function from reals to reals, and then, you know, you want to, like, or, you know, who knows what, like, it could get complicated, and it's just irritating to have to constantly deal with that technicality. So we just kind of ignore it, and most of the time it just doesn't end up mattering. The reason I really bring this up is just because if you're not aware of these technical distinctions, then if it ever does end up mattering, which sometimes it does, right, you won't know how to resolve whatever issue you might be looking at if you don't know the underlying distinctions that we make, the underlying technical framework that we work in, right? So you have to really learn all these like annoying formal technicalities before you can safely ignore them, kind of, to some extent at least. I mean, in this case, it's like, this is pretty benign. You can probably figure out how to talk about whatever you want to talk about with a function like e to the x, but it's just good to be aware of this stuff because, or just to always have it in the back of your mind that these kinds of things, these kinds of issues sort of lurk in the background, okay? So yeah, but I mean, I will say, like, I will never deduct points or anything from a solution if you pretend that you can invert a function that's like injective but not technically surjective because you never said what the codomain was or something. I'll never, like, actually, that's not the point of this. I'm not saying you have to constantly write in your proofs that, like, you have to restrict the codomain of f to be like the positive real numbers or whatever the, you know, whatever it is you're talking about. That's not the point. The point is just to give you, like, the framework, the general context of how we talk about functions, so that you're equipped to handle any situations you might find yourself in. Okay, so that's you know, in injectivity, surjectivity, bijectivity, inverses. Okay, so now let's talk a little bit about restrictions and extensions, right? So given f from S to T, and let's say U is a subset of S, then the restriction of f to u, which we write like this, is, sorry, it's like a comma, is the function or sorry, the restriction, the value of the restriction okay. So this is supposed to be a capital U down here as the subscript, and then of course we're evaluating at some point little u inside of capital U. So I'm just defining a new function. Now this is actually more important, okay? So I know I just got done talking about how we can kind of hand wave stuff about like the codomain, right? Like, is the codomain bigger or smaller? Like, if we're trying to invert a function, we can just ignore points in the codomain that are not, do not occur as values of the function or whatever, right? But the domain is sacred, okay? You don't mess with the domain without talking about it, okay? You can't just ignore stuff about this. You can't sweep this under the rug. If you mess with the domain, if you restrict a function, if you extend a function or whatever, that is absolutely critically important to talk about, okay? Or to like, unless it's extremely obvious what you're doing, okay? Or at least to bear in mind, you know, you have to think about this. You have to be careful about it, okay? So, okay, what now, well, okay, yeah. So this is a restriction, okay? This is a restriction from f from a larger set to a smaller set. Literally all it does is it defines a new function whose domain is just this whatever subset you were looking at, and it has the same values, right? So for example, you know, f of x equals x squared on r. You can restrict this to, you know, the non-negative numbers. Right? The graph here would be a full parabola, and then the graph here would just be half the parabola, including this point at 0, right? So, and this takes f from being not injective, right, to injective. So that's important, right? So restriction can radically alter the properties of a function. I think that should be fairly obvious. And so, well, this is just important because, you know, we do a lot of stuff in this class where we talk about like uniform continuity on a set or continuity on a set or whatever, anything where you're talking about like some subset of the domain, a property that f has on a subset of the domain. And it's like a lot of the time, those properties, you could also just think about them as like a property of the restriction of f to that subset, basically, right? So like continuity, like f is continuous on S, a subset of the domain of f, if and only if f restricted to S is continuous on its entire domain, right? That should be pretty obvious, actually. With uniform continuity, there are some subtleties that I think I talked about in the video about uniform continuity. So I'm not going to talk about that here. But with normal continuity, you know, this is pretty straightforward. And so restriction, you know, could be a handy way to sort of like change, you know, notationally manipulate this idea, I guess, or just to understand it. Okay. So, and then extension is kind of the opposite of this, obviously. So extension, we already even talked about extension. Like, so if f is a function from S to t and S is a subset of some other set U, then G from U to T is an extension of F to U if G of X equals F of X whenever X is in S. Okay, so if G agrees with the values of F at every point where F is defined, but then G also has some extra values at new points that F doesn't, where F isn't defined, then G is called an extension of F, right? So of course, if G is an extension of F from S to U, then F is the restriction of G from U to S, right? That should be hopefully fairly clear. But you should note there are usually many, let's just say many extensions of F from from S to U. So, you know, given F, we have no idea what it could have been an extension or what it could be a restriction of, basically. I mean, there are many ways to extend it. You can just define new values however you want, right? So there are many ways to extend F. But if you start with G as a function on U, there's only one way to restrict it to the subset S, right? That's just, you know, so restriction is always like a deterministic thing. Extension you can do in many ways. Of course, when we talk about things like continuous extensions and stuff, then when it's more constrained, maybe there's only one extension that has a special property you want. But in theory, you know, at least if you take this as a definition of extension, then there are infinitely many. We don't talk about extensions in general like this, like in math. It's not that common to talk about just like random extensions of functions in a totally abstract way, the way it is to talk about restrictions. Restrictions are a very common thing to talk about even in the most abstract settings, but extensions not so much. So that's extensions and restrictions. I want to just kind of tie a couple of things together now with these examples. So say F is defined from R to R. F of X equals X squared, right? Then F restricted to R greater than or equal to 0 as a map from R greater than or equal to 0 to R greater than or equal to 0. Okay, so when I say as a map, right? So normally when I restrict this, if I restrict F to the non-negative real numbers, right? Technically the codomain is still all of R. But what I'm going to say is if I restrict the codomain, right? Because all the values of F are non-negative anyway. So I can just throw out all the negative values from the codomain. And then I have this function. The restriction here is a function from R greater than or equal to 0 to R greater than or equal to 0. And that function is actually bijective. This is what we define as the square, root, right? So the function g of x equals square root of x, right? That's only defined. So here's f restricted to r greater than or equal to 0, right? And as you can see, here's g. And it's also a function from r greater than or equal to 0 to r greater than or equal to 0, right? So it was only after restricting both the domain and the codomain. We started with a function from r to r. We restricted the domain and the codomain to be the non-negative real numbers, and then we ended up with the bijective function. That was how we defined the square root, okay? Of course, I'm not saying you don't have to talk about any, like, you don't have to use this as your definition of the square root or something like that. I didn't even prove that this is actually bijective anyway. So, I mean, we can just take for granted that the square root is a perfectly, you know, that it has this definition basically, or that it has all these familiar properties. But I'm just saying, formally speaking, this is how the square root function is really sort of defined, is that, you know, or at least this is the only sense in which the square root can really be considered the inverse of the function f of x equals x squared, right? Because it's not truly an inverse of the entire function. It's only an inverse of a piece of it, of the restriction here, okay? So anyway, so that's yeah, all that stuff. The last thing I want to talk about is images and inverse images. So images, inverse images. Okay, so let f be a function from S to T, and then say A and B are subsets of S. Or let's say, okay, for now, let's just say let A be a subset of S. Then the image f of A of the set A is the set consisting of the values of f at every point in A. Okay. So if you ever see a set being plugged into a function, just remember that the result of that is another set, right? Always. Even if there's only one value, okay, even if f is just constant on A, there's only one value in here, the result of this is still a set. It's just a singleton set. It's the set containing one element. It's not actually like the value itself, okay? I mean, at least really technically speaking, like being really sort of legalistic or formal about it, that's what you'd say, right? Obviously, you can still talk about it being a singleton and having only one value or whatever if you want. So that's the image. So if, let's say B is a subset of T, the inverse image of B, written F inverse of B, is the set of all x in S such that f of x is in B. Okay? So now, very important, f need not be invertible for this to be defined, right? Very important. In fact, this is defined for an arbitrary function f. Literally any function, you can take inverse images of sets, okay? And notice that, like, if f is not surjective, say B could be a subset of T where like no values of f actually land in B. Then the inverse image is just the empty set. So that's perfectly well defined, okay? So it's always like, and if f is not injective, so maybe two elements map to the same element of B, then those two elements are just going to be in the inverse image, right? So it makes sense in literally any context, okay? Now, if one thing you can say is if f inverse exists, then f inverse of B, the inverse image, let's say, okay, let's give, just to avoid the confusing notation. So let's say if f inverse exists, call it G, then f inverse B, this is the inverse image, equals G of B of B under F. This is the image of B under G. Okay, so this is just saying that like we have these two concepts here, right? One is like mapping a set forward through a function, and one is taking a set and like bringing it backwards through a function. So what I'm saying is that if f happens to be invertible, then if you calculate the inverse image of some set in the codomain, just in this normal way, without like where you ignore the fact, just completely ignore the fact that f is invertible, but just find the inverse image of some set the way you normally would, it's, the set will be the same as the set you get by actually taking the function, which is the inverse, and then mapping the set in the codomain forward through the inverse function, according to this definition up here, right? Those will be the same thing, okay, when f inverse exists. But of course, most of the time, f inverse will not exist, okay? So like as an example, let me just draw a picture. All right, so here's just an example of like, if you imagine a function, you know, well, I don't know, I kind of visualized s and t on these axes basically, right? And so here's just a piece of t, just a subset of t. And to find the inverse image, you just look at all the places where f happens to be in that subset, right? Where the values of f happen to be in that subset. And then you just like collect those all together in a set. So that's the set you'd get for this picture. I think it's fairly straightforward, fairly self-explanatory. So now there are some important little, you know, pieces of sort of set arithmetic that you can do with images and inverse images. So first of all, so things to check. So in general, right, if you take the inverse image of f of let's say f of a, you will get a set which contains a, but may not be equal. Okay, you should just verify this for yourself. All right, these are all things, they're simple, you know, very simple little logic puzzles, not really even puzzles, but yeah, they're very simple. You should really check these for yourself. I'm not going to be able to give examples for each one. Similarly, actually, just by the same token almost, f inverse of b is always a subset of b, but these also may not be equal. F of a union, let's say a1 union a2 is equal to f of a1 union f of a2. F of a1 intersect a2 is a subset of f of a1 intersect f of a2, but may not be equal. F inverse of b1 union b2 equals the union of f inverse of b1 and f inverse of b1 intersect b2 equals the intersection of F inverse, F inverse of B1 intersect F inverse B2. Okay, so inverse images play very nicely with the basic operations of sets, union, and intersection, right? Images, not so much. Close, but there's this slight issue with intersections that can be very, very annoying, I guess. but inverse images are sort of more natural in that way. So let me think. I think that may be everything that I wanted to say. All right. Yep. So so that does it for this video. Anyway, I hope this was helpful, especially for those of you who might not have some of this background already. So yep. See you guys in class.